Hey everyone, we are part of Dr. Scott's EDAD 6331 course consisting of Mr. Tom Brown, Cody Martin, and myself, Richard Vela, and we will be presenting on multiple linear regression, which is a statistical technique that uses several explanatory variables to predict the outcome of a response variable. And now I'd like to go a little deeper into that. So what exactly is MLR? So this technique is used to model the linear relationship between a single dependent variable, which is the outcome we're trying to forecast, and two or more independent variables, which are the predictor variables. So when would we use MLR? So this can be used when we want to know how several factors concurrently influence an outcome and understand the impact and direction of each factor's influence. So what types of data can we use for MLR? The dependent variable must be continuous as any value within a range, right? This can be interval or ratio, and examples are like weight, test scores, and even satisfaction treated as continuous. And I say that because we're actually going to be measuring satisfaction in our demonstration. The independent variables, which are the predictors, can be continuous or categorical. Continuous, these are like numerical values. Examples are like temperature or income. And categorical, which must be converted to numerical format, for example, using dummy variables. Nominal or ordinal. Examples are like gender and education level. So let's talk about a scenario that we can utilize so we can use the analysis of the MLR. So, for example, the Dean of Graduate Studies wants to understand what elements influence graduate students' overall satisfaction in doctoral programs. The Graduate Studies Department seeks this information to provide and improve support systems and program effectiveness. The purpose is to gauge how well predictors such as GPA in a continuous 0 to 4.0, faculty support using a Likert scale 1 to 5, administrative responsiveness, also using a Likert scale 1 to 5, student weekly workload, hours per week, for example, 0 to 60, and program type that can predict the graduate student satisfaction. So as we go through this demonstration, we're actually going to walk you through the SPSS portion. This will include the data set, the SPSS analysis, and then we'll return to the slide deck to talk about the data output. So Cody, if you will, you can go ahead and share your screen for the SPSS demonstration.
Yes, sir. No problem. So we're going to get started. Hopefully you guys can see that. That is the data set there in SPSS.
Got it.
So this is what it would look like when if you were to say download it and open it there in SPSS. You have your data view, and if you come down to variable view, you can see all of our I guess variables, you could say, whether it's faculty support, administration response, workload, program type. So if we were to say our values for say faculty support, one, say a scale of, you can, depending on the data set, right? Ours is 1 to 5, 1 being very low, all the way up to 5 being very high. So if say a student gets more faculty support, that the more support they get, the higher that number could be. Um, we have another, our program type, since our data is only including the master's and doctorate, so those are those variables you'll see in our data set when we run those. So, but all these can be found in the variable view on that data set, and then these are subject to change depending on uh, what data set you run in SPSS. But for our demonstration, this is our set. So, but I'm going to walk you through the steps on how to run our multiple linear regression, right? or the MLR, as Richard was noting it earlier. But so first up, we're going to run to our top tab up here. We're going to run to Analyze, right? And from there, we're going to find our Regressions tab. And since it's a linear regression, we're going to run it from right here. We're going to find our dependent and independent variables, right? So our dependent variable should be our satisfaction score. So that these variables are it's going to what is going to affect our satisfaction score, right? And those variables are going to be our cumulative, our faculty support, admin support, program type, all that. So you can click on one at a time and move them over individually. So you could move one over, right? Cumulative GPA or what and whatnot. Or you can click, say, one, shift, click another, the rest of them, and we're going to bring all those over there as well, right? So we should have uh, one dependent, four independent variables, I think. But from there, uh, Richard and Tom, how are we looking so far?
Looking good.
Okay, so now that we're all keeping up, we got our variables selected. We're going to click on our statistics to kind of pick what we want to show when we run this. I guess, regression. We want to figure out what's going to be showing up, and we're going to, pick the things that are going to show up when we run it, right? So we want our estimates clicked, our module fit. We want that clicked. We want our descriptives clicked, so that's going to pull up our descriptive statistics, confidence interval. We want those selected as well. Leave it at 95%. That's the default, so we're going to leave that there. We're going to have, what else might we need clicked? Durbin Watson, we'll click that guy. And then I think we're going to click this guy here. We want this diagnostics run as well. And from there, I think that should be all for this window. So we're going to click
Case-wise diagnostics. Let's do that too.
case-wise diagnostics. Okay, we want that guy as well. And we're going to click OK or continue for this guy. So once we click continue, we're going to go to plots, which will be right under our statistics, right? And we want our Y field. We want it to be this guy here. So we're going to click it, and we're going to have it on Y. And then we're going to have our X field to be the top one here. We're going to have it jump over to our X field. We want our histogram to show, and we want our normal probability plot to show as well when we run this. So we click him, and I think that looks all for that section, I believe. And then we're going to click continue again. All right, we're almost done. We've got one more thing to do. We're going to click save on that, so it brings up the next window and saves our previous inputs. We want our predicted values. We want it to be, let's say, unstandardized. Where's that at? There it is. We're going to click this guy. For our residuals, we want it to be standardized. So predicted values, unstandardized, residuals. Let's do standardized for that guy. And then we're going to click continue. I think that's the rest on all this screen. And then we're going to click continue. And then last but not least, we're going to click OK. And this should, quote unquote, down here on the bottom, run our statistics. And that brings us to our next screen, right? When you run that linear regression or multiple linear regression, it'll pop up. And if you follow our format with all the different elements, you'll get your descriptive statistics, your correlations listed as well. And all of these, Tom will dive deeper into when you do your write-ups for your class or for your specific data set, right? So it has some different variables in our model summary as well. One of the ANOVAs on there as well, our coefficients and our residual statistics as well. And it also brings in some of our plots, whether it's our histogram that was populated, our p-plot that also got populated when we selected it, and then last but not least, our scatter plot, right? So all those, depending on what you select on those clickable screens I just demonstrated, will show up. Depending on what you select, is what shows up when you run the actual regression. So, with that being said, here's what happens when you run it. Let's minimize this. Here's our data set that we ran it. And Tom is going to take over from here and he's going to run down the actual kind of the results and how you're going to populate it in your write up. So, Tom, take it away for us.
Okay, Cody, thanks. Good job. Okay, can you guys see my table descriptive statistics there?
We sure can.
Great.
That
We'll
looks
go
great,
from
Tom.
here. Now, I'm going to be pretty literal and go through these pretty fast, but this is like when you would have to do your write-ups. This is what you would add to the tables that Cody just showed that were produced by SPSS. We'll start with descriptive statistics, and you will see that N is 45 for every variable. And for every variable, we have a value that is not zero. Our dependent variable satisfaction score, the mean is 76.22. The standard deviation is 10.115. And since all variables are, all values are greater than zero, the non-zero assumption has been met. So when we start to fill in our assumption data, that gives us information for that. And then moving on to the table 2, correlations. This will be in 2 parts. I'm showing the whole thing here. And I'll go to the next slide for the notes because we've got such a full screen here. We have our Pearson correlation information. We have the significance, one-tailed significance information, and you can see that for the satisfaction score, which is our dependent variable, that they're all less than 0.0001. And for N, everything is 45. So we have a complete data set there. Then we'll talk about the Pearson correlations part of that table. The color coding is from our spatial student version, V31. It's actually V31.0.0 parentheses 117 close parentheses, but it's a student edition of SPSS. You can tell even without the color coordinations, without the colors to tell us that these are very high correlations, both positive and negative. The green shows positive correlation, the red negative, but they're still highly correlated, almost too highly, which are very strong, near perfect correlations. And this, of course, shows that we have a problem with multicollinearity. So that is one of our assumptions that will not be met. And this is especially strong among, say, the GPA, faculty support, and admin responsiveness. Our range is from 0.874 to 0.988, just too much. You can see that we have the pale green and the pale red that shows lesser correlation, but that's just a relative thing. If we had smaller numbers that were actually what a statistician would prefer, those would be bright green, bright red, just if they were that high. It's just a relative thing. All of these are extremely high. The since the correlation extends from -1 to 1, we would normally expect these values, at least some of them, to be much smaller than this. Now, fortunately, since this is not really our data set, we don't have to talk about cause, why these are this way, but it makes you wonder if there's not some overriding factor here. since this data set was created by human beings, they had to think about what would be related to satisfaction score or what might impact the satisfaction score, which almost guarantees that they're going to think of things that would probably be correlated with satisfaction. And these things also might be correlated with each other. So not only that they correlate with the dependent variable, they correlate with each other, which is statistically considered not a good data set. Moving on to table 3, model summary R squared. The regression model yielded a multiple correlation of R equal 0.993 and an R square of 0.986, indicating that 98.6% of the variance in satisfaction scores is explained by the predictors. Yes, it's explained by all of them, but it is explained by the predictors. The adjusted R square of 0.984 confirms that this explanatory power remains robust after accounting for model complexity. The standard error of the estimate, 1.271, you can see right here on the chart, the graph, suggests a tight fit between predicted and observed values. The Durbin-Watson statistic of 2.184, shown here, supports the assumption of independence of errors as it falls within the acceptable range of from 1.5 to 2.5. Then our table 4 shows the analysis of variance. The ANOVA table confirms that the regression model is statistically significant. F 5 and 39 equal 549,594. And P, the significance probability, is less than 0.001. This indicates the set of predictors, and we'll list them here: grade point average, faculty support, admin responsiveness, weekly workload, and program type collectively, I'm glad we got to use that word, explain a significant portion of variance in satisfaction scores. The mean square residual, right here, 1.615, aligns with the standard error of the estimate, which is given on the previous chart, and is 1.271, suggesting a tight model fit. So tight, they all work together. Table 5, coefficients. Significant predictors for GPA, P equal 0.027, which means that it is a statistically significant positive predictor. Weekly workload, P less than 0.001, means that it is a significant negative predictor. Non-significant predictors, faculty support, P equal 0.661, administrative responsiveness, P equals 0.334, and program type, whether master's degree or doctorate, P equal 0.313. And we're going to continue the discussion of that, of table 5 coefficients. There is severe multicollinearity, as we said before. VIF, which is variance inflation factor, is one of the columns that we're going to look for on this slide, along with tolerance. The VIF for GPA is 58.229. Weekly workload VIF equal 58.626. Admin responsiveness VIF 20.278. Faculty support VIF equal 15.836. Program type VIF equal 4.954. And this is only elevated multicollinearity, not extreme as the others are. It's less extreme than the others. It's all All predictors except program type exhibit severe multicollinearity with VIFs exceeding 10, that's the accepted cutoff, and tolerances below 0.1 in this column. So this compromises the interpretability of individual coefficients and violates the assumption of no perfect collinearity. For table 6, collinearity diagnostics. Notice that GPA and weekly workload both load heavily on this unstable dimension, suggesting they are structurally collinear. Their shared variance is inflating standard errors and destabilizing coefficients. Faculty support and admin responsiveness also share a high variance. High condition index dimension indicating redundancy and suppression effects. Our condition index, down at the bottom here, equal 256.621, and our shared variance proportions in all of this are greater than or equal to 0.5. Table 7, residual statistics. Residuals range from negative 2.616 here is a minimum to a maximum of 2.588 with a mean of 0 and a standard deviation of 1.197, indicating that prediction areas are errors are symmetrically distributed around 0. Standardized residuals range from negative 2.058 on the year to 2.036, falling within the conventional plus or minus 3 threshold, suggesting no extreme outliers. The standard deviation of residuals, 0.941, is close to 1, supporting the assumption of normality. Predicted values span a wide range of 58.03 to 91.64, consistent with the observed spread and satisfaction scores. So the good news here is that we have normalcy in this data. Figure 1, the histogram that Cody showed you briefly. This histogram with standardized residuals shows a fairly symmetrical bell-shaped distribution with a mean near 0 and standard deviation near 1, supporting the assumption of normality. Figure 2, normal PP plot. The normal PP plot confirms that residuals closely follow the expected normal distribution. They're right along this diagonal line like they should be. And figure 3, scatter plot of regression standardized residual. The scatter plot of standardized residuals versus predicted values reveals a random, evenly dispersed pattern around 0, indicating that residuals are homoscedastic and that the model's linearity assumption is upheld. Okay, as a bonus, we're going to include a discussion of the assumptions for this, and there are quite a few. Well, they cover two pages here. The variable type assumption is met by determining that the dependent variable is scale, while the independent variables are both scale and dichotomous. The non-zero variance assumption is met since the descriptives output shows a variation across all 45 cases. The assumption of no perfect multicollinearity is violated since VIF values are greater than 10 for 4 of the predictors. The condition index, as we saw on the charts themselves, condition index equal 256.621 shared variance proportions greater than equal to 0.5. The assumption of predictors not correlated with external values is assumed to be met to the extent possible. The predictors were selected based on theory and prior research. As far as we know, this not being our data set, but a sample data set that we were able to obtain. No known omitted variables are strongly correlated with either the predictors or the satisfaction. The model is not intended to make causal claims, only to explore associations. This one, predictors not correlated with external variables, almost seems impossible to me. You can't know what you don't know. You can't know that there's not an overriding variable that all of these things are reacting to. For instance, if you had a good measure of attitude, if you could measure the attitude of all those students, could they be driving the selections made by the students on all of these tests? But again, let me go back and say these are not intended to make causal claims, so I'll get off that and move on. The assumption of homoscedasticity was met since residuals are evenly spread across predicted variables. The residual scatter plot shows uniform spread across these predicted values. And to continue the assumptions, the assumption of normally distributed errors or normality of residuals was met since the histogram of standardized residuals and the p-plot indicate that the residuals show approximate normality. Standard residuals are approximately 2. The assumption of independence of observation was met by design in which there were no repeated measures or clustering in the design. And finally, the assumption of linearity was supported by a residual scatter plot that shows random dispersion. A strong R-square, 0.986, supports linear fit. So with that, I'm going to turn it back to Richard.
Great. I want to make sure that you all can see my screen.
Yes, conclusion.
Great, great. So thank you so much, Tom and Cody. And now we'll kind of just, in conclusion, cover that the multiple regression model was statistically significant and explained nearly all variance in satisfaction scores, leading to rejection of the null hypothesis. Although the model demonstrates strong overall predictive power, high multicollinearity, I hope I said that correctly,
Yes.
among predictors limits the ability to interpret individual coefficients accurately, as Tom covered. When multicollinearity occurs, two or more predictor variables in the regression model are highly correlated with one another. When predictors overlap in the information they provide, the model does struggle to determine the unique contribution of each variable. So in this analysis, although together the predictors explain a substantial amount of variance, the high shared variance between the predictors show the coefficients cannot be interpreted independently. So we want to also mention that as part of this exercise, we will also be submitting the data set that we utilized for this exercise, along with a note-taking document that kind of follows along with this particular presentation. We also want to highlight that there is actually a step-by-step SPSS input navigation guide that we found to be very, very helpful with this exercise. So we hope this presentation was helpful to you as you continue in the advanced data analysis course, and in particular with a multilinear regression analysis. So with that, we will go ahead and stop our recording. And thank you very much.